I am Koit Saarevet. I work for the National Archives of Estonia. My career there spans 2 millennia. I started in the year 2000 as general IT manager, and pretty soon I moved to the core business side, started to develop the digital archives infrastructure and various software components. And for the past couple of years, my job title has been the head of database preservation, which is the reason why I'm here today to tell you a few words about how we preserve databases at the National Archives of Estonia. While it is kind of from the Estonian perspective, the core of the talk is actually applicable to basically any environment, any country, any type of organization, whether it's government or business, doesn't matter. The technical tools and key concepts are the same. I am going to cover this from different angles, and so here's the table of contents. So first I'll start from the legal foundation. What gives us the right and the reason to archive any databases at all? Then the second is to give scope to the technical talk is a few words about database models and which specific models can be addressed using the tools that we cover today. The third one is about what to archive, again, from the technical perspective. If we have an information system that stores data in a database, then what parts of this information system do we archive? Fourth is about the process, like organizationally, what actions are done by which parties and in which order. Fifth is about metadata or descriptions of various kinds. And finally, the sixth is the most important and most interesting part. How do we actually do it? Really, what buttons are clicked and what commands are issued? Let's then move to the actual content. So the legal foundations. The very basic question, why do we archive anything from any databases at all? The answer is that some databases do contain information that has permanent value. And in the context of Estonia, the legal definitions of it are given in the Archives Act, which is kind of the most how to say, powerful legal act that regulates archiving in our country. There is, quite in the beginning of this act, we could also call it Archives Law, but the official translation to English is Archives Act, but it's basically a law. So the first or the second paragraph in this law is about the definition of information and records and archival records. So subsection 2.1 says that the record is information recorded on any medium. So it's a super broad definition. Subsection 2.2 says that archival records are records to which archival value has been given by an appraisal. And subsection 2.4 says that archival records created in the course of public duties shall be transferred to the National Archives. Now, when we think about these definitions, then the first sentence here says that the record is recorded information. So databases do record information, so they fall under this definition. The second one is that some records are given archival value through appraisal. Again, this can happen for the databases as well. And the third one, that if the database has been created in the course of performing some public duties, then it has to come to the National Archives. So we have the legal grounds, but that's at the level of the law, which you can read in English under this link. An important idea here is these appraisals. So how do these happen? Appraisals are done by the National Archives of Estonia. We have something called appraisal committee that makes these decisions. And the archival value can come from three types of situations when we look at in the context of databases. The first one is in the year 2017, we did a very broad analysis of all the publicly registered information systems in Estonia. We have a special registry for all the government information systems. It's called something like State Information System Management System, basically just a catalog of systems. And there were about 1,000 of them at the time. And then we went through this whole list and looked at what type of data is managed in each of these systems, and then determined a very short list of them that we considered to have really, really super important information that is valuable even through centuries. And at this point, we ended up with 26 databases only out of this 1,000. Then the second source is we also have appraisal decisions specific to organizations. For instance, every public university in Estonia, we have made an appraisal decision specifically about their records. So these specific appraisal decisions can also give archival value to specific information systems that were not covered for some reason in this in the general one that I mentioned earlier. The third source is sometimes any kind of appraisal decision, whether it's for a specific institution or a specific field. For instance, we have an appraisal decision for healthcare records, or we have a decision about IT management records, wherever they're located, regardless of the organization. If it's a public sector organization, they always manage some IT records, and we have this thematic appraisal decision about it. So if in one of these appraisal decisions, a certain set of information has been given archival value, usually it's arranged into a series in the archival sense. So if this series is moved from the traditional documents that are managed in a records management system into a core business information system, then fundamentally nothing changes. The information is still there. It's exactly as important as it was previously. So now the database where this information is managed will also get archival value, or at least a subset of the database. This information of archival value that moved into this database. So these are the three core ways of these appraisal decisions. You can read many of our appraisal decisions at this link. I will show you the page. This is transformed into English using Google Translate. So the terminology is a bit messed up. It's not evaluation, it's appraisal decisions. But yes, here is one decision about how we mapped the whole country, all public agencies. And somewhere here is the one that I mentioned, the number 51 from 2017, about all the databases registered in this state catalog of databases. And then there are all these other kinds of decisions also visible here. Now to move on, we have also an information system called Astra, which is our tool for managing work with agencies, our sources of ingests. And in this system, we have a special section for handling data about databases. And this system then has a page which lists all the currently recognized databases of archival value. And at this point, there are 78 of them. When we go to this page, here is it. You can see it's 78 items. And that's the sort of official source of these databases. So we can try to look at, for instance, National Forest Resource Accounting Registry. I will show you some documents about this registry later. We call it just Forest Registry. So this got its archival value from the same general appraisal decision. Okay, so much about the legal basis. Let's now move on to the more technical side, database models. There are many database models in existence. Historically, it started from very basic ones like tree structures. For instance, a family tree can very easily be expressed in the form of a binary tree. And there is this one root, me as a person. I've got two parents, so two lines come out of my little rectangle in this tree, and then each of them also have two more branches coming out. A very easy structure. Methods have been for managing it already in existence for, I don't know, almost a century. But there are also all kinds of other these data model types. For instance, object model is very widely used today, where you don't need to think much about the structure of the data objects that you store. You just have a huge barrel where you can just throw your objects in. So developers can use these programming language objects, like a person object that has attributes, name, birth date, contact data, etc. They can just throw these objects into this huge vat. But they can also 5 minutes later decide that they also need to store information about buildings, and then just start throwing these buildings objects there. They don't need to redesign the database. But the first one here, relational database, this is a very strictly structured thing, which was invented about 50, 60 years ago with the purpose of efficiently managing large quantities of structured information. So it had to be fast, it had to be free of all kinds of anomalies like duplicates that conflict with each other, and also this transactional integrity that to guarantee that when multiple users are accessing the database at the same time, they always see the same truth, and when one user does some writing actions, then it doesn't affect others, and so on. So that's why relational databases became very, very popular, and they are today, still half a century later, the main data model that is used for large information systems. So basically, we can talk about two categories here. The first is relational, and the other, which is like a list of 20, can be called NoSQL. What is SQL? It is a structured query language. It is a technological language to talk to databases. And the most famous command or sentence in this language is select asterisk from something, somewhere. What it means is select indicates that we are selecting some data out of a huge quantity of data in our database. From indicates where we are taking it from. So city in this case is the name of a table. And the asterisk says that we want all attributes from that table, all columns. So we could also select only the name of the city, but in this most basic syntax, the command takes all the fields from the city table. And it also does it for all rows, because there is no specification here how to filter the rows. So relational databases are manipulated using the SQL language. And that's also the reason why they are kind of used synonymously. Oftentimes people say, I am using an SQL database. And they mean that it's a relational database that uses the SQL language. Also, a lot of products, database products, have this SQL in their name. For instance, Microsoft SQL Server is a name of a product, and people often even say SQL Server, meaning Microsoft SQL Server. So it's a tricky term. You need to be careful to not misunderstand the meaning of the speaker. But what is this NoSQL then? NoSQL has got two definitions. One is non-SQL in the sense that the database that is not relational, not using the relational data model. And the other one is not only SQL, meaning that the database might be able to speak the SQL language, but it has maybe some other languages that you could use, or it has some attributes that are not fully covered by the relational data model. Our tools that we discussed today are not suitable for most of these NoSQL databases. So we are focusing on the relational ones. Now, what are these relational databases? The first important characteristic is data is stored in tables and columns. So there is a very clear table structure in every relational database. Second is the way relationships are created in a relational database. For two tables to be related, there must be identically fields in each table that have identical meaning, the same semantics. For instance, the tree structure, the binary tree example that I gave, you don't need any like matching attributes there. It's in the basic definition of a binary tree that each node has two arcs coming out of it, two lines. But in a relational database, you can have unlimited number of data attributes. They can be linked to unlimited numbers of other attributes in other tables. And the way the links are created is by having a column with the same meaning. And here is a practical example of it. This picture is called entity relationship diagram. So each of the rectangles is an entity, and we see here three entities: city, country, and country language. The database itself is called world, which is a sample database that was created about 25 years ago for testing and teaching purposes. And its greatest value is its simplicity. It's very easy to understand what's in here. It's just data about countries and cities and languages. And when we look at the city and the country table, we see that there's a line connecting them. Unfortunately, this specific tool that I used to create this diagram does not connect the line between the specific fields that are connected. It just draws it between the entities, the rectangles. But basically, the link here is created using the code in the country table and the country code field in the city table. So these two actually have exactly the same meaning, that there are some kind of identifiers in the country table, and when you want to show that a city is located in that country, you will enter the code for that country into this country code field here. Now, next topic. What do we archive if we have an information system? When you talk to IT people and ask them what should we archive, then oftentimes their first idea is, let's archive the whole thing. I mean, we usually manage information systems in either virtual machines or containers. We can just archive these, and then whenever we need them, we just pull them back from the archives and launch them, and everything works as before. And it's actually a usable method. For instance, this image here is from a real public registry in Estonia that operated in the beginning of 1990s. It's used to manage certain legal documents. We had this property reform. We needed to return the property that was forcibly taken away by the Soviet occupiers in the 1940s to the rightful owners when we regained the independence in 1991. So this database was kind of managing part of this information that was used in the property reform. And back then, the dominating operating system was MS-DOS, basically a text-based system, a black window where you just could type commands in white letters, and there was no graphical interface. Usually there was no mouse, nothing to touch on the screen, just commands. And this environment, although it operated on very slow and very unresourced computers, it could actually be used to do a lot of meaningful and valuable work. And one of the enablers of this valuable work was a program called FoxPro, which is a database engine created by Microsoft. And this specific version, as you can see, operated in MS-DOS in text mode. And the information system, it contains data with archival value. And we actually archived the whole information system. And it is still operational in our systems. We have a server, and in the corner of that server runs MS-DOS and this FoxPro system. And when we get queries from our customers, we have trained an archivist who is able to do queries using this user interface that you see on the screen. Of course, we also archived the data properly using all the decent long-term database preservation principles. Back then, it was CSV files for the data and SQL files for the structure and queries, and also a lot of textual documents in the form of PDF files to describe the meaning of the data and the operation of the system. This method, unfortunately, is not usable anymore because systems have gotten too complicated. And here is an oversimplified picture of a modern information system. It's hugely oversimplified. But nevertheless, you see, there's a lot of stuff here. Of course, any information system operates with data, so it needs to have a database engine. And inside that engine, we have the data in the form of zeros and ones. It's encoded in binary system. Also, the system always needs to have user interfaces. In the modern times, we have many of them. Every system has public web interfaces, or actually, I would say most systems have. Or if they don't have a public one, they have an internal one for the employees, but most government systems have both. More modern systems have also interfaces for mobile devices, specific ones to the platforms. To make these interfaces work more efficiently, to not repeat tasks that are needed often, then there is something called application server, or these middle layers where some of the frequently used operations are done, so that they need not to be programmed into every one of these separate user interfaces. Then we also have some kind of APIs, application programming interfaces for connecting to external systems. Then usually the websites, they are designed to be scalable so that if the demand rises, for instance, the tax office, every year people need to file their tax returns sometime in the spring. The demand goes to the sky. Then it's there for like 2 months. And the rest of the year, nothing really happens there, but the system still needs to be alive. So there are these methods of launching web servers, as many as needed. So we need to have a bunch of web servers, but to do this on-demand launching, we need to have a load balancer. So a lot of complexity, but it's by far not all. There is more complexity in each of these rectangles. For instance, when we zoom into one of these web servers, then obviously it has to have an operating system. Then there is a programming language framework there. Then it's the actual application code. Then there is the web server software that is the tool that talks to the customer's browser and so on. And when you look into each of these rectangles here, again, there are other components there. So in the end, a modern information system consists of hundreds and hundreds of components. And consequently, nobody has figured out a way how to keep this complexity functional over the long period of time. Because all these components need to be kept up to date. You cannot just statically archive it. If you do the virtual machine snapshot, put it on the shelf, then after 10 years, maybe the operating systems have changed too much, or the hardware has changed too much so that you cannot run your own old operating system there and so on. So it's a dynamic job and therefore too complicated and expensive to perform. What we do instead, when we look at this information system stack here and the archive, we actually archive only the data from the database into a special archival format called CIAD. But to have some context about the whole thing, we also archive data descriptions, which is, of course, also very much needed for understanding the data in the CIAD file. And from these other layers of the system, we take just documentation, what was there, how it functioned. And to have some visual memory of what was there, we asked transferring agency to create these little videos of user interface operation. Somebody who knows the system well just does the day-to-day actions there and comments it with their own voice. And the purpose is that future users can get a better sense of what was there. The data archiving part is highly automated. So basically just a few commands are given and then the software does all the work. But these upper parts involve manual work by archivists in the agency and at the archives, at the National Archives. Now, what is CIAD? This stands for Software Independent Archiving of Relational Databases. This technically means that we liberate the data from the stranglehold of specific database engines. In active live database engines, data is stored in binary format, as I said, and this format is specific to that database engine. For instance, I cannot take the data files from an Oracle database engine and put them into the folder where I have Postgres database engine installed. Postgres will not be able to understand these Oracle files. And even worse, we cannot use Oracle data files with another version of Oracle database engine. So this is obviously a very bad situation for long-term archiving. We are locked into a very specific version of specific software. So CEARD is independent of these restrictions because it's a plain text file in XML format. And you can see here that it's, in addition to being machine readable, it's also quite human readable. Like the tag here, DB name, kind of hints that it's the name of the database. This FR stands for Forest Registry. That's the abbreviation that is used for this database. And the description is a bit longer name of the database. And then we have the archiver field, and then further down there are descriptions of all the data tables and relationships, and even further down is all the actual data. CEARD has become the de facto standard for archiving relational databases, which to my knowledge is used by most of the organizations that do database archiving for long term. It was created by the Swiss Federal Archives about 25 years ago. The first, stable or official version came out in 2004. And it has gotten several updates over time. And for the past about 11 years, it has been managed or developed by this eArch consortium, which is also the entity that is currently operating the European Union e-archiving initiative. And this consortium has a special body called the DILSIS board, which is a team of very smart people who maintain all the standards that have been adopted or created by the eArch Foundation. So you can read the CEARD specification at this address. Now to the process. In Estonia, we have this more or less established process. It's not like super well polished yet because we haven't had enough volume, but it's more or less this way in most cases, and it can be categorized into 9 distinct steps. The first step is initiation, which means we gather information about the database that is about to be transferred and establishing contact with all the right people. Second is a kick-off meeting where we introduce this 9-step process. We discuss access restrictions and we agree on the next steps to be taken. Step 3 is cloning the database, which means that we make an exact copy of the database to be archived so that we have 2 instances of it. The reason we do it is that while archiving is happening, the creation of this CEARD file, it is important that the data does not change in the database. Otherwise, there will be broken integrity. And the easiest way to achieve it is to just clone the database and then do the archiving work on the clone, which is installed somewhere in a peaceful server where nobody touches it. In live databases, like core state information systems, changes are always happening. So when the clone is done, second step, or in this list, fourth step is to produce this test snapshot, which means that the agency that is transferring the database needs to install the database preservation toolkit somewhere close to the server where they have the cloned database data. Then something called the YAML configuration file is created, which makes it easier to automate the work and to do repeated snapshots if more tests are needed. I'll show you it later. And then a snapshot is created, a CEARD file, which contains all the tables and views from the database, but only the first 1000 rows. Then we look at this snapshot at the archives, do some appraisal decisions. Maybe some technical tables can be left out, for instance, some access logs or whatever. Then sometimes we do a second snapshot, sometimes it's not necessary. Then we again look at it if everything is correct. When we have determined that now it's all as it should be, then we do the final snapshot. And after that, we make sure that we have gathered all the necessary documentation and also finalize the archival descriptions. And the last step is formal signing of this instrument of receipt or instrument of transfer and receipt, which is this legal declaration that the National Archives now has received and properly stored the database so it can guarantee preservation. Now to descriptions. This here is Rosetta Stone, which is a famous piece of rock, which includes one text in 3 different languages. So the upper 2/3 of the stone is the text in ancient Egyptian languages, written in 2 different Egyptian scripts. And the bottom is in ancient Greek. And the reason I'm showing it to you is that this stone was the key piece of information that helped to learn how to understand Egyptian hieroglyphs. So basically, it's an example of badly done archiving. The texts were unreadable for many hundreds or even 2000 years until in 1800 this stone was found and this the next year. So in the archives we operate with very long time frames. So this here is the sign of infinity. So we need to make sure that our data is understandable and findable across very long time spans. So we need archival descriptions. Here are the usual elements of it from the ISAT-G standard that most archives use. Our description standard is also based on ISAT-G. It's more or less compatible. So we always have these basic elements filled and sometimes even more detailed elements. So for every archive database, we need to have archival descriptions. But as I said previously, we also need to have technical documentation. For instance, data models. There are 3 kinds of them, and they are usually expressed in the form of these documents that list all the tables and all the fields in the table. Also, we want to have these graphical entity relationship diagrams, which I also showed you for the world database. But we also take all kinds of other documents, like data descriptions are very important. The more detailed, the better, to explain really the semantics of each of the data fields in every table. And it's good if there are ontologies, which are some sort of systematic pre-made trees of terms. We also take architecture information for context, although we don't archive the software, but still for the user to understand the whole system, it's useful. Also, user guides are useful, and many kinds of other documents that we can get our hands on. Okay, now to the tools. This black creature here is a software bug. I'm going to show you actual functioning software, so usually something goes wrong, so I apologize in advance. The first tool is called dbeaver. dbeaver is a database administration tool, which is open source software. You can download it and install it for free. It allows you to talk to many different database engines. The list is really long. I think like 50 different platforms are supported. All the free ones like MySQL and Postgres, but also the commercial ones like Oracle or Microsoft or IBM. It looks like this, not very friendly to the eye of an archivist, but IT people love such views. Everything is very well structured, easily understandable for them. For instance, on the left-hand side, you have this logical tree of all the objects that are in this specific database. We have the tree for world open. There is a folder for all the tables, and we see there is a table called city and tables country and country language. And under each table, you can open the list of all the columns and so on. And then you can issue SQL commands, and then in the bottom area, you can see the results. And here's another screen of it. So now I will show you the actual dbeaver. So here it is, very much the same view. So I'm connected to the world database now, and I can here issue the SQL commands. So select asterisk from city, as I said, brings out all the rows and all the fields from the city table. When I want to filter it to some narrower set of data, I can say that where name equals Tallinn. And now I get all cities that are named Tallinn. Now, when I want to understand what country is where this city of Tallinn is located, what is this est thing? So I can do it in a dirty way by remembering est and issuing a query to the country table, where country name is est. Was it for some reason it doesn't give me the right answer? That is super weird. Let me check if I have the syntax correctly. Excuse me, wrong field. It was supposed to be code, not the name. So I was looking for code equals est. The name is Estonia. So that was the dirty way. But the more cleaner way is to create this nested query, where I first use one query to look up the code for country where Tallinn is located, and then look all the data from the country table, which gives me the same row as you see here. I can also do more cleaner output, like for instance, look up just the name of the city and the country, like that. So SQL has got all these capabilities, but in order to use it, you need to learn SQL. So next step is the archiving part. Before we get to that, we have a guide for that created by my colleague Lauri Rätsep. He produced this little helping document, which is an instruction guide for the IT guys on how to do this CR file. So they don't need to invent everything by themselves. They can just read the instructions. But basically, where we now go to is the database preservation toolkit. And here I can click on the create button, go to MySQL, which is the database engine. Type in these parameters for connecting to the database engine. And database is called world. And now I click next. It now connects to the database and queries all the information about the structure. And it shows that it's got 3 tables. They have relationships between them. Now I can click next. I can create custom views, which I don't want to do now. I also don't want to have this Merkle tree but I need to give it name for the database file. So it will be a cert file. And now I can enter some etc. Not important to fill them now, but in real life you would want to give proper metadata. And now the tool connects to the live database engine, and it has already now produced the cert file. And I can tell it to import it for viewing. So we can see how the same world database looks in the archived form. Here you can see the metadata, which I mostly left empty. And when I click browse, now it's going to index it for full text searches. So for large databases, it can take many hours, but for this small one, it's just a few seconds. And now here we have the database structure. These bubbles, their size indicates the number of records. For instance, a city table has over 4,000 records, but country only has 200 something. And the color indicates how many relationships to other tables they have. So the darker the circle, the more connections. And when I click on circle, I can get the listing of all the data there. Now, when I click one of the rows, I can see the details, and I can also go to related tables. So the best way to show it is, let's again look at Tallinn. I want to get data about Tallinn. And I searched it, and it gave me the result that the city table has record Tallinn. And now the same task we had before, I want to know what country is it. So I now don't have to write any SQL sentences. I can just click on this blue link, and I'll be taken to the details of the country. So you see that actually it is much easier here in this software to explore the data in the archived snapshot than it is to do it in the live database. Now, next, I want to quickly show you the command line tools, because this graphical thing is nice for basic experimentation, but not so good for professional use. So we can do exactly the same thing by launching this command, which is super complicated at the first glance, but when you start to analyze it, it's very clear and logical. This first sentence says that we are running a Java program. We are using UTF-8 encoding. That's the actual program file. And then here are all kinds of parameters. These are database connection parameters. That's here is the metadata, and that's the name of my output cert file. So when I enter the command, it does something, and now we have the database file. So here you can see that's the first one we created before using the graphical interface, and that's the one I now created using the command line. And the file size is exactly the same. But in reality, we also want to do some changes in the configuration. So for that purpose, some of the configurations we could do by tweaking these command line options, but it's much easier to have a text-based command or configuration file. So in reality, what we do is we use another command, which does not create a cert file, but creates a configuration file. So this parameter here says that we export not the cert file, but we export the configuration file. And here's the name of the configuration file. So now the tool connects to the database engine and produces a configuration file that contains the structure of the database. So here you see this conf YAML. And that's how the YAML file looks in the inside. It's got the general parameters and then the data about all the tables and fields. And here you can do some tweaking. And the typical tweaking that we do is that we, for the test snapshot, we limit the number of rows that we get. So by adding these few words here, now the city table is not exported entirely, but only the first 1000 rows. And now I can run the command to create another CRT file which uses the configuration file that I just created. So you see, as import, it takes this configuration file as input for importing the data. And the result will be called world test snapshot. Okay, let's run the command and see what happens. We now have world test snapshot. And when you look at the size, you can see that it's now only 411 kilobytes. It's much smaller because we limited the number of rows here. I'll also show you how it looks inside. So we can unzip it, and inside, basically the CRT file is not actually just a plain XML file. It's a folder structure where there are several XML files and they are zipped together. So inside the CRT file, you have these two folders, header and content. And in the header folder, there is a file called metadata XML, which is where the structure is described. So in the beginning is the general metadata, and then we start having these data tables. So here we can see the table city. So this blue part is now all about the city table. So for each field, we have the field name, data type. Is it mandatory? Can it be zeroed? Here is the name field. It's 35 characters maximum, and so on. And in the end, we have information that 1000 rows were archived from this table. And we can now go back to the tool. Let's do open CRT file, and let's import this test snapshot. So it's the same database as I created here in the graphical one previously, but now I created it via command line and with a restriction of only 1000 rows. So here you can see the similar structure description, but when I hover on the city table, I can see that there's only 1000 rows. And otherwise it's still the same, but the bad side effect is that I have lost Tallinn, because Tallinn is in the very end of the table. But many other cities are still here, so I can see the general structure and I can still check the links between the tables. Okay, so that much about the tools. The Database Preservation Toolkit is free software. It is created by a Portuguese company. Let me get back to the slide. Yeah, so that's the address where you can download it. It's able to create CRT files, make them viewable, make them searchable using a simple full text search, and it visualizes the structure. And you can read more about it at these addresses. One important feature of the tool is that it can create CRT files from many different source databases. And it can also load the CRT file into many other database engines. So you can basically create a CRT snapshot from an Oracle database and then load it into, let's say, Postgres SQL database if you want to get rid of Oracle license fees, for instance. You can migrate your data into an open source database engine. And the instructions for using the system are very easy. This is a brief overview of what you need to do to use the graphical interface. And here is the instructions for the command line, which is a long list of descriptions of all these parameters that I showed you, and many more. Very easy to use for IT people. Okay, that is it